Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week. And I wanted to just start off here before we get into the subject matter as to why sometimes there are these delays. In theory, the videos are supposed to come out Monday, Wednesday, and Friday, and sometimes they don't make it on those days. And what happens, to be perfectly honest with you, is I have an idea in my mind what I want to do. But then once I get into the graphical production of what I want to try to show, it ends up taking way more time than I originally think it's going to take. And the nice thing about the bonus weather videos is that they're not time sensitive. So it's not like back in my days of TV that I couldn't show up at 4 o'clock and say, can you give me just a few more minutes here, because everything had to go out at a certain time and had a certain length of time, and all of that was predetermined. But the nice thing about this is that if I run into some, extra time that's needed to produce the graphics, that it's not the end of the world. At least I don't think it is, as long as I get you the 3 by the end of the week that I promise you that I would get you. So just wanted to, give you an explanation on that. And I am a bit of a perfectionist. That's one of my many flaws. And so once I start making these things up, I keep thinking, oh, I could do better here, and I could do better here, and then it ends up taking 6 millenniums instead of 20 minutes. So let's go on ahead and put myself down here in the corner. And we're going to talk about relative humidity and something called vapor pressure, okay? So we have to start off with some definitions, as you might have expected. So the definition, the ratio of the vapor pressure of water to the saturation vapor pressure of water at a given temperature is the official definition of the relative humidity. Okay, now we're going to get into what vapor pressure is and the difference between regular vapor pressure and saturation vapor pressure and all that stuff in just a second. But that is the official definition of relative humidity, is the vapor pressure compared to the saturation vapor pressure. Okay, now in simpler terms, it's simply the ratio of the amount of water vapor in the air to the maximum amount that can exist at a given temperature. And as the temperature warms, there is the capacity for more and more water vapor to exist. So, and we'll get into that as well in just a little bit. So basically, relative humidity is the ratio between how much water vapor is there and how much could be there if it was maxed out at a given temperature. Okay, does that make sense? Okay. Now, the saturation vapor pressure is determined by the temperature. The temperature basically makes the rules in terms of how much water vapor can exist in the atmosphere at that particular temperature, okay? So that's sort of like the benchmark, the high end. And then the vapor pressure itself is determined by the dew point, which is the absolute amount of water vapor that is actually in the air, okay? So the saturation vapor pressure is the maximum amount, the vapor pressure is the actual amount. And if the two are the same, then the air is saturated. So what the heck is vapor pressure anyways? Well, here's the official definition. Now don't get scared here, just bear with me. The pressure exerted by a vapor which is in thermodynamic equilibrium with its condensed phase, in this case liquid water, at a given temperature in a closed system. What the heck does all that mean? Well, if you have, like, say, a glass of water, and you have liquid that fills up, half of the glass, and then the rest of it is just air, but there's water vapor in that. So if it's in thermodynamic equilibrium, it means that there are as many molecules that are escaping from the liquid state to the vapor state as there are condensing from the vapor state back to the liquid state, okay? So the overall water level is not changing, okay? You've got as many going out as you do coming in, okay? And that's what thermodynamic equilibrium is defined as. So the pressure that is exerted just by the vapor itself is the actual vapor pressure, okay? Now, let's take a look at a tall glass here, okay? And we've filled it to that level with liquid, okay? And so we've got liquid there. Now, we're going to put, I guess for lack of a better word, like some sort of a plunger in the top there. Anything that will completely close off the system to the outside world, okay? So in other words, once you put that little blockade in there, if you will, then the whatever is underneath that blockade is not exposed to the outside air anymore. Okay, it's a completely closed system. Now, what you do in that area where there is vapor, but it's closed off to the outside world, you're going to remove the air from that area and create a vacuum, because you don't want to find the pressure of the air in there. You want to get rid of all the air so that you can see what the pressure of the vapor is after the air has been removed, okay? So that's the way you would do that. And so in that area then, all that's left is the pressure that is exerted by the water vapor itself. Okay, so here is a graph of the saturation vapor pressure, which again, remember, is determined by the temperature. The temperature sets the tone for how much water vapor can exist. And then the temperature in degrees Celsius is there along the x-axis. And the blue line is the saturation vapor pressure, and then the orange line is the vapor pressure if the relative humidity was 50%, okay? But the one thing that's important to notice here is that both of them are not linear, okay? They are increasing exponentially with that increase in temperature, okay? And this is going to be a really, really important point that I'm going to make here in just a second. Now, standard atmospheric pressure is 1,013.2 millibars at sea level, okay? Well, let's go up the y-axis here to about 1,013.2, just above the 1,000, and take it over here and see where it exists with this saturation vapor pressure curve, and then go down that line and see what the temperature is. Well, it's 100 degrees Celsius. Well, guess what that is? That is the boiling point of water. 212 degrees Fahrenheit, but 100 degrees Celsius. So the boiling point of water is defined as when the vapor pressure is equal to the atmospheric pressure. Okay, that's how the boiling point is actually defined. All right, so that's just a graphical way of showing that. Okay, so what I did here was I actually made some calculations, and I converted the temperature to Fahrenheit, so it's a little bit more familiar. And they are not exactly 20-degree increases, but they're close. I had another table where I had a bunch of numbers, and I simply picked out the numbers that had the closest difference of 20 degrees that I could find. So let's take a look at a 20-degree jump here, or almost 20-degree jump, from 32 to 51.8. Well, both the vapor pressure and the saturation vapor pressure increase by a factor of about 2.15, so it almost doubles with that 20-degree increase. Then, if we go from 51.8 to 71.6, which again is almost a 20-degree increase, we increase the amount of water vapor in the atmosphere and the saturation vapor pressure as well by a factor of 2.01. And then if we do it again from 71.6 to 91.4, itchy eye here, then we increase it by a factor of 1.9. So if you average all of that out, for about every 20-degree increase, every 20-degree Fahrenheit increase, we are doubling both the saturation vapor pressure and the vapor pressure, okay? And that's for a relative humidity of 50%. But you could do it for any relative humidity level, but the bottom line is those numbers are doubling every time you go up 20 degrees. So the last thing I wanted to show you here is simply a much simpler graphical way of looking at this. So we're going to look at 4 containers, okay? Each container is 50% filled with liquid, and each container is twice the size of the previous one. And this is what we just talked about in the previous table. So at 30 degrees, you have a container which is so high and it's half full, and so that's going to represent 50% relative humidity. And then at 50, you're going to double the size of that container, okay, which means that the liquid that fills up half of that container is twice the amount of liquid that was in the 30-degree container. Then, if you go to 70, you double that, and the amount of liquid that fills up the half of the 70-degree container is now twice as big as the 50 and 4 times as much as the 30. And then if you go all the way up to 90, the liquid that makes up 50% of that container is twice as much water as the one that fills up half of the 70. It is 4 times as much as the amount of liquid that half fills up the 50-degree container, and it is 8 times as much as the amount of water that half fills up the 30-degree container. So for every 20 degrees that you increase the temperature Fahrenheit, you are doubling the capacity of the atmosphere to hold water vapor, which means at 90, the same relative humidity. All of these relative humidities are 50%, okay, because all the containers are half full. But there's 8 times as much water vapor in the air at 90 as there is at 30, even though the relative humidity is exactly the same in all 4 of those circumstances, okay? And this is why I really push the idea of using dew point, because dew point is more like an absolute humidity. It's an absolute amount of water vapor in the air instead of a relative amount. You can have a temperature of 100 with a dew point of 70. Okay, so that's really hot and there's a lot of water vapor in the air, and the relative humidity for that would work out to be about 38, maybe 39%. Okay, and so you're sitting there thinking, well, that's not bad. That doesn't sound that bad. But meanwhile, you've got sweat dripping off of you because there's so much water vapor in the air that it's not evaporating. Your sweat is not evaporating off your skin nearly as effectively as if the amount of water vapor in the air was much lower. And so it just sits there on your skin and you feel miserable. Okay, but you're sitting there thinking, well, 38% doesn't sound all that high. And if you ever hear somebody say, oh, I remember that day when it was 100 and the humidity was 90%, that's never happened, okay? If the temperature is 100 and the humidity is 90%, that would mean the dew point would be up around 97 or 98. And so far as I know, at least in modern times, that has never actually occurred, okay? So relative humidity can be a very, very confusing thing, but the dew point temperature is an absolute measure of moisture in the air, and for every 20 degrees the dew point goes up, you're doubling the amount of water vapor, and again, that's what really dictates your comfort level in terms of how effective the atmosphere is at evaporating the perspiration off of your skin. Okay, I know that was a lot, okay? I hope at least, well, let's use one of the terms in the video. I hope at least 50% of it made sense, okay? And that way we'd be relatively in good shape. All right, that is it for now, folks. That is bonus weather video number 1 for this week. Number 2, we'll try to get that out on Wednesday on time. And the next daily update, of course, coming up later today. So you all have a great Tuesday, folks. We'll talk to you soon. See you later.